We'll go ahead and get started. We'll have Zhengyu Liu and Jianjia Yu present on the domino effect. Let's clap it up for them.
Hello, everyone. Should we get started? Okay. So, hello, everyone. Welcome to our talk, The Domino Effect, Automated Detection and Exploitation of DOM Clobbering Vulnerability at Scale. So, I'm Zhengyu Liu, and this is my collaborator, Jianjia Yu, and this joint work with Tao Li, Zifeng Kang, and my advisor, Yingzhi Cao. And we are both PhD students from Johns Hopkins University, focused on web security and software security. And we spent our most of time studying vulnerabilities, building security testing tools, and thinking about how to make the modern world a better place. And today, we're excited to share our research on DOM clobbering. So I will first start a very quick overview of what DOM clobbering is, and then explain the challenges of detecting those vulnerabilities at scale, and introduce our automated analysis framework, HAWK. And after that, Jianjia will take over to present our large-scale zero-day hunting results and show how we turn those HTML injection into the end-to-end exploits with DOM clobbering gadgets we find. So let's begin. So DOM clobbering originates from an old but still standard browser feature defined in the HTML specification. And it allows you to perform named lookups on window or document objects to access elements on the page. While this feature provides a convenient way to reference like DOM elements by their ID or name, it often opens the door to the DOM clobbering attack in the scenario where those elements are attacker-controlled and it wasn't the developer's intention to use them at all. By crafting a name collision between the DOM element's ID or name attributes and a property accessed via like the window or document, the attacker could pollute the JavaScript value and change the application logic. So, and especially modern web applications often accept a wide range of user inputs, including like scriptless raw HTML to support things like rich text formatting or like embed media. For a more concrete example, to give a illustration for people not very familiar with this is that at first the attacker needs to inject an A-link or element to the page. And then the page contains JavaScript that probably reads from like window.remote to load additional scripts. And if this is undefined, it fallbacks to use like a CDN URL and load script from there. However, with the attacker inject link whose ID equals to the remote, the lookup is no longer undefined, and instead it refers to the injected A-link, and this is what we call a clobber. And later, like when the DOM element is concatenated with a string, type coercion occurs, and for those link elements, this converts them from a DOM element to their ref value, and producing a URL controlled by the attacker. And finally, the URL flows to the script.source and resulting in loading malicious code from attacker's domain. Since DOM clobbering was first introduced by Grace Hayes in 2013, a lot of work has been working towards understanding various clobbering techniques. And at the core, the key question is which HTML markups can clobber which JavaScript targets and probably under which browser implementations. Because clobbering behaviors is defined in the HTML specification, but the browser implementation may vary slightly. And building on years of the findings and also the updates from the browser, the recent paper from Auckland 2023 called "Is Clobbering Time?" is the first to systematically answer this question. It uncovered like over 30,000 clobbering capable HTML markups across 5 distinct techniques, making a real scientific forward in this field. However, identifying those clobbering behavior is just the initial payload landing step of the attack. And for the full exploitation, we still need the gadgets and the exploits. So the following question is, can we automatically detect those gadgets and generate working exploits so that we can really testing them at scale and better understand its landscape in our modern web? And this is where our work comes in. So to do that, there are two main challenges. The first one is that real-world JavaScript, especially after minified or bundled, is full of dynamic behaviors like aliasing or directed property lookups. And it's very unfriendly to our static analysis tools. And those features make it extremely hard to track how data flows through an application, and in turn makes the gadget detector a very hard problem. The second challenge is exploit generation. In DOM Clobbering, the payload is no longer a string, which is usually the case, but it's a DOM element. And that elements need to be compatible with the JavaScript operations in the gadgets and carry the attacker-controlled values to the sensitive sinks. And if the element itself is malformed or is not incompatible with the gadgets, it may break the code and just fail to propagate the payload. Okay, now let's take a look at a motivating example and show how those challenges failed our existing approaches. This is a zero-day cross-site scripting caused by DOM Clobbering found by Hawk in my favorite platform, HackMD. The HTML injection was possible because the developer allowed the name attributes on the iframe tag, unknowingly exposing its application to the DOM Clobbering. To escalate the HTML injection to cross-site scripting, Hawk found a vulnerable gadgets from the Google Client API library used in the page. And the Google Client library is used by a website that tries to integrate the Google service like Google Drive, Google Maps, or YouTube. And once the library is loaded on the page, it will process the developer-defined configurations in the page and callbacks embedded in the page, and by searching the corresponding script tag that contains the configuration URL. And then we'll use a new function, which you can dynamically generate a function, like generate a JavaScript code, by parsing those configuration objects and execute its code. But here's the problem, that the source it uses, document.script, is vulnerable to DOM Clobbering. So the attacker can inject a clobbered DOM element that is not a script, like an iframe with a crafted name equals to the script to hijack the configuration object. And combining the HTML injection and the DOM Clobbering gadgets in the page, the attacker could achieve cross-scripting by sharing a malicious HackMD nodes and probably perform any unauthorized actions on behalf of the user. And till now, both the HTML injection and DOM Clobbering gadgets have been fixed by the HackMD and the Google respectively. And let's talk about the private work. The thing is a static analysis tool that tries to detect this by looking at the source code. But it fails to detect it because of the dynamic behavior and condition logic embedded in the gadget code. Secondly, exploiting the gadgets requires HTML marks that satisfy both the data flow and control flow constraints along the chain. The data flow constraints ensure that the payloads can flow from one attacker-controlled variables to another, while the control flow constraints ensures that the program state execute the JavaScript, execute the gadget's logic, so we don't execute it earlier. For example, the constraint 2 involves a subscript operation of the clobber value. So this means our clobbered objects must behave like a collection, such as HTML collections. If it's just a single element, the access on it will throw a runtime error, and the gadget log will just fail to execute. And the thing fails to generate a working exploit because it only considers the initial clobbering pattern, but ignores all the constraints in the gadget code. And as a result, it produces payloads like image name equals to script that will never reach the sink. Another popular client-side testing tool, DOM Invader from Figler, failed to detect it is because it relies on a canary-based testing. While this approach works very well for string-based exploits by checking whether partial attacker-controlled value reach the sink, it does not apply to DOM Clobbering, because DOM Clobbering requires a near-correct HTML element and considering all the constraints from the gadgets. And randomly generated HTML will just never reach the sink. Or even worse, it will just break the website functionality and skip executing many real gadgets. Okay, Now let's see how we solve the problem with Hawk. Hawk operates in 3 stages. So our key insight here is that instead of directly injecting HTML markers from the start, we first perform the tint tracking on website-defined values from those potential clobberable source to the sinks. And this phase is non-intrusive and helps us identify a wide range of potential gadgets without needing to guess the payload. And next, based on the tint trace, we extract the data flow and control flow constraint and use them to generate the corresponding exploit markups. Finally, we insert those craft markups to the page and replay the execution and check whether the payloads reach the sink, confirming whether the gadget is really exploitable or not. Specifically, in the first stage, Hawk performs dynamic tint analysis on website-defined values. We categorize the source into 2 tabs. First, the lookups on document can be directly shadowed by the attacker-injected values, like document.links, document.streaks. And in this case, we can directly tint the original values and observe how they propagate in the program. And second, there are lookups on like a window object where the attacker clobber value is only used if the original value is undefined. And this is typically appear in like those fallback expressions like ternary operators or like logic or checks. And in such case, Hawk will track those fallback values instead and identify opportunities where the attacker-controlled value might take effect. And Hawk will only inject its own value, like random value, when there is no website-defined value is present as a fallback. The sinks used in our tint tracking are typical like client-side sinks, like inval, set, timeout, and others. The tinted value in the page are managed in 2 ways. For objects with properties, we just insert another like specific field, a non-enumerable property, so that it doesn't interfere with the normal program behavior. For those primitive values, which are very hard to be tinted, we wrap them with a special object that holds both the concrete value and its tint metadata. So this allows us to track even undefined values. Our tint engine supports propagation across JavaScript operation, built-in JavaScript built-ins and browser-native APIs, and so on. And the tint propagation rules are implemented in a very extensible way, like adding support of a new APIs is as simple as defining a single handler function. And we implement the tint analysis using a code rewriting approach based on Jianjia instead of instrumenting the browser itself. It gives us a very flexible feature and allows us to track all types of JavaScript values and supports cross-browser analysis without relying on the browser internals. The output of the first stage would be the tint trace represented in a tint dependency graph. And the backbone are the operations, and there are concrete values and also the attacker-controlled tinted values. Next, the challenge would be, once we have this tint dependency graph, like how do we generate the HTML markups that can leverage those operations observed in the graph and carry the attacker-controlled string all the way to the sinks? And in the second stage, in this stage, like we will introduce the concept of a symbolic DOM, which allows us to formally define the constraints that DOM elements must satisfy at each step along the path. And then we implement a simple DOM constraint solver that uses those representations to automatically generate the compatible and exploit-ready HTML markups. So the first step, to model, so we need to understand what a successful exploit would look like. So to model a valid exploit, we treat the HTML payload as flowing through 4 key stages in the tint dependence graph. The initial clobbering, where the attacker's DOM elements first inject to the JavaScript program. The advanced clobbering, where some parts of the first injected DOM elements get loaded and to the program. And the third stage is DOM to string, where the string payload loads from the attacker-controlled DOM elements to the page. And the final stage is string to string, where the string is processed or transformed and finally flows to the sink. In the first stage, the DOM elements should contain an ID or name attributes correspond to the name, the lookup keys, which is quite straightforward. On the second stage, the attacker-controlled elements must be further loaded. And this stage is only necessary when there are additional JavaScript operations before the string payload can be loaded. And since we cannot skip any JavaScript operations in the graph, so we need to use this advanced clobbering techniques to fulfill them. And the problem would become if the base object is an attacker-controlled DOM elements, how do we form it in a way to make the results of the operation could also be attacker-controlled DOM elements and without raising any error? And there are a few strategies can be taken. The first way is HTML injection, that you can inject multiple DOM elements with the same name attributes and it will look like an array. The second way is to use the well-known nested window proxy, parent, child, or input form those relationships to clobber lookups, whose property is a general string. And the third way targets a certain DOM-specific properties like previous symboling, and by arranging the DOM elements to match the expected structure. And later on, when the attacker, there might be several rounds of advanced clobbering, and later on the attacker needs to load its string from the controlled DOM elements to the program, because the final payloads shown in the sink should be in a type of string. And there are three main ways to achieve this. The first is the well-known technique through type coercion during binary operation like add. And it applies to the A and area elements, where accessing those elements and triggers the use of its ref value as a string. The catch here is the ref value must be a valid URL, and browser will often auto-fix it with a protocol like HTTPS or whatever is used in the current page. And to bypass this, attacker would need to inject a base tag before the clobbered element, controlling how those relative URL are reserved. Another two-stage operations can be leveraged are function calls and get field, which is less documented. For the function calls, some JavaScript built-ins and browser APIs would automatically coerce its arguments or property values to string. So in that case, if the attacker control value is passed to those or accessed in this way, the browser would perform the coercion just like those during the binary operations. The third way is to exploit the attribute name collision. Like if a property name matches to a legitimate reflected DOM attribute, it can be abused. For example, if the application reads the value property from the element, then the attacker could inject an input tag with a payload saved in its value attribute because it's a valid attribute name. And our paper includes a comprehensive list of those attributes and APIs can be used in this stage. And finally, there would be a rise of a string-related transformation and finally flows to the sink. Okay. So we know what a legitimate DOM elements should look like. To describe those in a formal way so that we can solve them, we need this symbolic DOM syntax. So it's basically a constraint syntax to describe a set of DOM elements with the same list of features. And it comes 4 primitives int, boolean, string, node, and a collection. And each node represents a DOM element which can have a tag name and several attributes. And a node can have siblings and children. And a valid symbolic DOM that can be concrete to the HTML must have one root node. And then with each operation type and also the stage we just mentioned, we could generate the constraints on the inputs or output elements used in the operations. For example, to achieve document to DOM through the document.p operation, the DOM elements can be described on the page. Whereas the is root has tag name and has attribute constraint. And when p equals to the script, so we can concrete to a very simple HTML element. And with those model constraints, we can traverse all the operations nodes and attach those constraints to the attacker-controlled nodes. And each attacker-controlled node in the graph should have 2 conjective sets of constraints, as it serves as the return value of its precedent operation and the arguments of the subsequent operations. And finally, we need to merge and solve those constraints. And the key insight here is that we start from small and then connect the dots and finally concrete to the HTML. So what does it mean? It means that first we focus on the local constraints like C1 and expand it into a disjunctive norm form or DNF form. And in this form, each local constraint can represent a valid, possible DOM trace that satisfies those constraints. And next, we will merge the formulas across different DNFs if they point to the same tinted nodes. And during this process, conflicts may rise, and we just need to get rid of them and only save the valid combinations. And you can think of the second stage as attaching different DOM trees at their shared nodes, and discard any combination that doesn't fit together. And in the last step, we will just concrete the formulas to the HTML marks as input as exploit. And finally, in the last step, we would just inject our generate payload and replace the web page and see whether our canary value from the exploit could really flows to the sink. And next, I'm going to hand over to my collaborator, and she will show the results. Okay.
Hi. All right, so let's get to the real exciting part. Now I'm gonna show some real-world examples we found with our tool Hawk, as well as some. So those include some DOM clobbering gadgets in the wild, in web applications and libraries, and also end-to-end exploitations. So first, we apply our tool Hawk to Tranco top 5,000 websites and found 497 zero-day exploitable gadgets. So our cases includes modern web bundlers like Webpack, RSPack, Vite, TSUB, Polyfuse, and some core functional libraries like Prism, PageFind, MathJax version 2 and version 3, and also some third-party services including Plausible Analytics, Google Client API Library, and also web application frameworks like Astro. Our dataset is public. You can access the whole dataset through this QR code if you are interested. So the first case I want to show you is the Webpack. So according to an investigation, there are an average of 1.27 Webpack bundles per site among the Tranco top 100K websites. So this vulnerability we found by Hawk can lead to cross-site scripting on websites that uses Webpack as the bundler. So in case you're not familiar, so the pipeline of using Webpack is like this. First, you have to feed the website source code to the Webpack to generate the production code, which includes the compressed website code and also the Webpack runtime code, which is the Webpack library code. And in that Webpack runtime code is where we found the DOM clobbering gadget. So with that DOM clobbering gadget, if that website contains an HTML injection, this gadget can cause cross-site scripting. So let's jump into the code gadget. So Webpack requires the developer to set the public health to be auto, or you can either leave it to be empty in hope that the Webpack will help you load some external scripts. But actually, it is doing more harm than you think it is doing good. So if we pay attention to the code itself, in the first box we marked up, so the document.current script can actually be clobbered. And then in the box 2, the script URL is loaded as the document.script.source. So in this case, if we construct our payload like this with the source equals to https://https attacker.control.server, that script URL will be an attacker-controlled control URL. And then later, finally, this script URL is used as the Webpack require.p, which will be later load that script from that attacker control domain. So that will cause arbitrary script loading from the attacker server. So the second case I want to show is the Astro. It is a widely adopted client-server web framework to help you construct a web application from scratch. So in this code, we can also find DOM clobbering gadget where the clobberable element is here the document.scripts. But this case is a little bit special. So if we pay attention how the document.script is used, we can see it is accessed through array.from. So the code is treating the document scripts as a array, not just one single HTML element. So in this case, we have to construct the payload as an HTML collection instead of just single one HTML element. So, and then if we jump into the for loop to see how do we reach the final sync, we can see two conditional checks before we reach the sync. So the first condition check checks whether the script.dataset.astro.exec is equal to an empty string. And the second condition checks check the type, which is an attribution, which is the type attribution of the HTML element we got before. So to bypass those two condition checks, with our payload, the first script.dataset is undefined. So the first condition will return false, which causes the code to continue execution. And then when we reach the second condition, the type, again, in our payload, the type attribution does not exist. So the second condition will also return false. That will finally lead us to the final sync, where the new script is created as a new element with a script type, and then its inner HTML is copied from the payload's inner HTML. So finally, we can achieve arbitrary code execution if we construct our payload as this HTML collection. So in our case, the inner HTML will be alert 1. That causes the cross-site scripting. And then the final case study I want to show you is the UM editor. It's an editor previously maintained by Baidu. So in this code, it's a little bit straightforward. So if we can see the clobbable element is the window.umEditor_home_URL, which in our case will be the HTTP attacker.control.com. And then later, that variable URL is used to be assigned to a global variable, umEditor_config. And then later, that variable is concatenated with some constant strings to construct the final URL that the code will be loading the script from. It is also causing the scripts being loaded from the attacker's domain. So finally, I want to talk about the end-to-end exploitation. So to understand the end-to-end exploitation, we first need to achieve HTML injection. So as mentioned before, the web application, they accept and process all sorts of user inputs. But how does it become unsafe? So we have some basic findings. So first, some sanitizers from these websites, they do not strip the ID or name attribution by default. And the web applications, they're not aware of this DOM Clobbering vulnerability, and they rely on those ID or name attributes for intended logic. So due to these reasons, the ID or name attribute, they sometimes slip through the whitelists as they don't seem harmful at all. So based on how these web applications process the user inputs, we categorize the input factors of HTML injection into two types. The first is by user typing and the application rendering. The second is by the user copy and paste HTML elements into the page directly. So the first case is easy to understand. The attacker might input some raw HTML strings, such as the image tag with source equals to X and on error equals to alert 1 into some user controllable fields. And then those strings are later parsed and rendered by the web application without proper sanitization. So the second input factor is to insert through copy and paste HTML elements into the page directly. This is based on several factors. The first is that the elements whose content editable attributes is enabled, they can accept HTML elements directly. And second is that the clipboard data can have text or HTML MIME type, not just plain text. And also the browser clipboard APIs, they would sanitize cross-site scripts, but they do not sanitize ID or name attributes. As mentioned before, they don't look harmful at all at most of the cases. So based on these factors, what if the website just saved these HTML elements input from the user or attacker without proper sanitization? That will cause the stored HTML injection. I will show you with one real-world example we found. So this is the Canvas LMS discussion at Jhengyu in our school. So in the discussion board, in the input box, if you just directly input some raw HTML text into the input box, they will be sanitized. But if you directly copy and paste HTML elements into the input box, the website will actually accept those elements and render those elements in the website. That will cause the HTML injection. This is usually caused by the web application developers. They are mostly cautious about user inputs by typing, but sometimes they are just careless about the contents from the clipboard. That's why it's causing HTML injection in this case. So we also manually hunted for HTML injection in the world in real-world web applications. So we manually discovered 187 HTML injection vulnerabilities in various web applications, including wiki, webmail, forum, editors, RSS, social media, chatbot, and so on. And we also summarized 12 editors and client-side libraries that are vulnerable to HTML injection. They can also be accessed in our public dataset. And then in terms of end-to-end exploitation, with all the DOM Clobbering gadgets we found by Hawk and also the HTML injection vulnerabilities we found manually, we can achieve 12 end-to-end exploitation with those gadgets and HTML injection. So those includes 11 of them leading to cross-site scripting and one leads to CSRF. And the affected applications include the Jupyter Lab or Notebook and also Canvas LMS. So let's dive into the Jupyter Lab or Jupyter Notebook for details. In summary, we found HTML injection in Jupyter Lab, Jupyter Notebook webpage, and also we found DOM Clobbering gadget with Hawk in MathJet, both versions 2 and version 3. The MathJet library is used by the Jupyter Lab to render mathematical formulas. And combining those two together, we can achieve end-to-end exploitation. So in terms of the HTML injection, we found that in the markdown preview page of Jupyter Lab, if we insert some, if we just type in raw HTML tags, for example, image or whatever HTML elements, it will be accepted and rendered in a web page. And we also reported this end-to-end vulnerability to the developer of Jupyter Lab. And they also confirmed that it is not trivial to mitigate this vulnerability because the ID and name attributes, they are assumed to work by a large number of widget libraries. So a very easy example is that, for example, there's a markdown file with 2 hashtags hello. This tag will be rendered as an H2 element with the ID equals to hello. And the ID hello will later or somewhere be used as the fragment identifier in the URL to locate that element in the page. So if we take a look at the MathJax library, it is a library widely used to render mathematical formulas, and it is used by the Jupyter Lab. So with our tool Hawk, we found DOM Clobbering gadgets in both MathJax version 2 and version 3. And just days before they released version 4, and they promised to fix this vulnerability, but we haven't checked yet. Just say good luck. Okay, so if we take a look at the MathJax version 2, we'll find the window.mathjax here is clobbable element. And then later that variable is concatenated with some constant strings to construct the file URL. And here a type coercion happens. And finally, that file URL is used to the script.source, which is to load the attacker-controlled scripts. that will cause cross-site scripting. And but if we take a look at the version 3, just at the first glance, there is no more global window.msjs, and there is no more loading of additional dependency scripts by default. But by leveraging Hawk, we found that MassJS version 3, they support using the require macro, which allows you to load extension scripts. So we further from that, in version 3 of MassJS, there is a global element called the document.currentScript. And then later that document.currentScript is document.currentScript's SRC attribution is get, and with some regular expression replacement operation, the string from that payload is retrieved, and then finally that t variable is assigned to the r.src, which is the SRC attribute of one script element in the page. That is also causing loading scripts from the attacker's domain. So okay. So till now, we have both DOM Clobbering gadgets from MassJS, both version 2 and version 3. And also with our research on DOM Clobbering, we reported those problems, and Firefox is also considering patching the DOM Clobbering by disabling the shadowing on document lookups. And they are referring to the zero-day gadgets found by our tool Hawk. That's good news. So to summarize, we design and implement Hawk, a dynamic analysis tool for automatically detecting and exploiting DOM Clobbering gadgets. And we also conduct a large-scale study over the Tranco top 5,000 websites and identify 497 exploitable gadgets, revealing the widespread presence of DOM Clobbering vulnerabilities in popular client-side libraries. And also, we demonstrate 12 end-to-end exploitations by combining the discover gadgets with real-world HTML injections, validating their practical impact. So our tool, the source code, the dataset, and the paper are all open source. Feel free to access them if you are interested. And also, both of us, Zhengyu and Jianjia, we are open to internship or full-time jobs. So if you have any opportunities, please feel free to reach out to us. Thank you.